should we flip through the answers?
Sure.
Should we go through these questions again or just go straight to the answers?
I think we can go through the answers right away. I mean,
All right.
Yeah, pretty fresh in my mind.
All right, so here's the statement, and we parse it. It starts, it's blue, so we have the blue, and then the for comes, and then the exists, and then a for all, and then an implies. So that's the parsing. And we start needing to prove this. And I guess the function is a free variable. So I guess I could have parsed it at the top saying that the free variable has to be specified by the universe. But here we have the free variable is being told, I guess it's not being told by an adversary, right? It's being told by a friendly oracle. We're told that what f is, right? And so we know what f is. And then we come down to the for all, and normally would say let x be arbitrary, but I've restricted it to x equals 0, and then the epsilon's arbitrary. And now we have to come up with a delta. So somebody was just saying that there's some hard place. Well, maybe this is the hard place. You have to come up with a value of delta. And so I magically came up with the third root of epsilon. And you'll say, well, why did I do that? Well, I guess let's go forward and see. The reason I did it is because it works, right? You go forward and then you say here, let x be an arbitrary real value. And then then it's the oracle's assuring us. So if she's assuring us, we don't have to do any work. We just say she's assures us that it's in this range. And then I have to prove this. All right, so here's, I have to bound this. Well, this is, we plug in our definition of x prime is still x prime, and f is x cubed, and x is 0. And so that's what we plugged in. And then it comes, right, this simplifies just to x prime cubed. And we come over to, well, x, so I guess here we have to say x prime is, we know it's less than or equal to x, so x prime is less than or equal to all this stuff. Well, x is 0, right? X is 0, so this is basically saying x prime is less than or equal to delta, right? So I'm just using the fact that x prime is less than or equal to delta to say that x prime cubed is less than or equal to delta cubed. And then, so
Wait,
then
hold
I
on.
plug in my value. Hello?
Sorry, the absolute value just kind of disappeared.
Um,
And that's kind of important.
well, all right. So let me fix that. Right? Isn't that, then that we need to say it's less than, I mean, then you could always do two cases here. What do we want to prove? We want to prove that the absolute value sign here. Oh, and anyway, actually, no, I take it back. I purposely made it equal a cube. So here, if, oh yeah, well, yeah. So actually, x cubed is going to have the same. All right, maybe.
I think if it was x squared, you could get away with this because x squared is always positive, but
Right.
x cubed is negative for half of its domain. And so it is a very different function when you take the absolute value.
All right. So,
But I mean, I think the proof ends up being
Alright,
about
so-
the same anyways. I'm just being a stickler.
you fine. We fine. We can fix it. All right. There we stick in x cubed, the absolute value of x cubed. And the absolute value of x cubed is going to be less than delta cubed because this is 0. And so it's between negative delta and positive delta. So the absolute value of x prime is going to be less than delta. So we get delta cubed. And then that's where you plug in the value of delta to give you epsilon. Oh, here's another typo. Oops. There we go. Was that too tricky? Anyway, what about this one? So here's we're saying for every function, if the function's continuous, then these a values converge, right? So we parse it. It's a for all f, and then we have a yellow side, and the yellow side has its for all blue, and has its exists yellow, and has its for all blue, and then has an implied, and the implied says that if the prover can prove this, then we will be assured of that. And then the blue side says it's a for all for blue is red, and the exists is blue, and the for all is red, and then we have an implies, so that if the oracle can assure us, then we need to prove it, right? People see the parse tree, and we start at the top. We need to prove this. So our oracle gives us an arbitrary function, and now we need to prove this. So the oracle assures us of the left side, and we need to prove the right side. And then we're given an arbitrary epsilon from the oracle, from the adversary, and then we get kind of stuck on coming up with the I, right? So we come over to the oracle, and the oracle is saying, give me a value of x and epsilon. Well, I think at some point I hinted that you're supposed to, you didn't need that it was continuous everywhere. You only needed it to continuous at 0, because that's where we're getting close to, right? So that hint then tells you to plug in x is 0, because we want to know that we don't care it's continuous everywhere. We want it continuous at 0. So we set x equals to 0. And what do we set our epsilon to be? Well, we get our epsilon from the other adversary. And then she gives us a delta for which this stuff is true. And now we have to come over and get an I. And if you come up here, you can say, well, x is 0, right? X is 0. And so our numbers here are our x primes are between delta and negative delta and delta. So this is our, and we see here x prime is kind of being compared to 1 over I prime. So if x prime is compared to 1 over I prime, and we need something to bound I prime, right? So it seems to be a flip of it. So here's a bit of a miracle. I guess you have to figure out to flip this over. And I guess I was hoping you'd see that you flipped it over. And then we come over, right? So that we are over here, we construct our I to be the flip over. And maybe one thing that's maybe it's hard for people, I don't know, is that if delta is close to 0, then 1 over delta is a big number, right? And I guess officially we should round it up to be an integer. But so I guess here we never, here our I doesn't need to be an integer. It could be a real number because we just need to be all integers. This needs to be an integer, but I prime needs to be an integer, but I guess I doesn't really need to be an integer. Anyway, I flipped it over. This is going to be some big number. And then we continue on. We let I prime be bigger, but I prime be some integer. And the adversary assures us that it's bigger than I prime's bigger than I, and I is 1 over delta, right? So that gives us that it's I prime is bigger than 1 over delta. And then now again we have to prove this, right? So we're stuck again. So we come back up here and we're able to give the oracle some value of x and some value of x prime, right? And again, there's a relationship here between x prime and 1 over I prime. So that's how we set x prime to be 1 over I prime. And then now it's a blue thing. The blue has to prove that x prime is in this range. And you can just sort of say, well, we have this relationship. And so if you sort of crank through, it sees that, yes, in fact, I prime is bounded like it should be. And then she then assures you of this, which when you plug in the values as necessary, you get what you need. How are people feeling about this? Was this too hard?
I mean, I was able to get it, but the algebra was definitely very tricky, and it was definitely like kind of seeing, oh, this has to be this, and you know, I almost felt lucky that I was able to kind of guess the right stuff early on. Right. I was not so lucky in the next question though.
No. All right, so we get these things. All right, so now we're trying to prove that I thought it has little arrows here, but I guess I don't know where my arrow went. But anyway, we want to show that f is continued at every rational. All right, so what's our parse tree? Here's our continuous parse tree, the same one we did before. And we get our dense parse tree. It says it's yellow, so the for all is blue, right? You can give the prover gets to give the x value, and she will return a c value between them, right? So here you can plug in any real value, and she'll give back a rational value that's in the middle. So what are we doing here? We need to prove that this thing is continuous. So we want to prove that. She assures us of this. Then we're given some x value and some epsilon value, and I think I gave you the hint that there are two cases and they're pretty much the same. So let's just assume that x is on this side. So we're given some x on this side, and what, right? What is all we need to do is prove that. Right? What do we need to prove? We need to prove that x is 1, right? Because Anyway, let's keep going here, right? So and then we let epsilon prime be 0, and then we come down and we try to prove this. So now we have to construct the delta. So we need to construct the delta so that for any range in here, anything in here has to have a value close to 0. Has to have a value close to 1, right? We have to say, give a delta, some range in here, so that for everybody in this range, the answer is close to 1. And so how big can this range be? Well, it can't be past this, right? It can go this way for infinity, it doesn't matter, but this way it has to be, it can't go past this number, right? So what we want to find is we want to find a number, a boundary that's in here. So we have to use this somehow. We have to give her 2 numbers. And what numbers do we have? Well, we only have 2 numbers, right? We have the square root of 2, which is conveniently a real number. And we have x, which is not it's irrational, so it's also real. So we give her these 2 numbers. And what does she give us? She gives us some number in the middle, right? Some number in the middle, there it is. And it's, right? And so then we say, right? Oh, and she assures us that it's in the middle. So then we come down, right, so then we come down to our delta here, right? We have to come up with the delta. And what's my delta going to be, right? It's this distance here. It's the distance between x and our c. And then we're given some value of x that's in this range. And we have to prove that it's, she assures us, right? We don't have to prove it. The oracle assures us that it's in the range. And then we say, because it's in the range, right? Because we're in the range, we know that x is bigger than the square root of 2, right? It's bigger than c. So it's bigger than the square root of 2, which gives us that its value is 1, and we have the difference between them is 0, which we never really used the epsilon, right? We got an epsilon from up here, but we never really used it because the difference is 0. How are you guys doing? Am I killing you here? I'm going to call you Naba because I don't know what else your name is. Am I killing you?
Yeah, it is Naba. It is Naba. Part of the question I got it right.
Right.
Yeah, it's just the continuous statement was hard a little bit to parse.
Right.
Yeah.
Right. So I guess people, I guess some of you, I don't know whether taking calculus would have helped or not. Maybe it would have, but you get these proofs thrown at you in calculus, and I'm not sure people know about how how you're parsing it and how the game goes. And so, people who took something like this in calculus class, can you follow these proofs?
It's that, when you do calculus, the way you teach for first order logic is different than how it's, and first of all, it's not taught like this, like in the detail in calculus, right? It's more 1019 where they teach.
Right.
So when you combine those two, the thing is the way you teach it, it's easier, or let's say it's not as difficult to understand as it would be if we were to put 1310 and 1090 to get 1019 together, you know,
Right,
that's what it is. So
right.
I guess, and my partner was is brilliant. So
Well done, partner.
yeah, Ali was
Conrad, right?
amazing. Ali.
Oh, Ali. Oh, sorry, Ali. All right, yeah. Yeah,
So,
Ali seems like they're brilliant. Yeah,
So yeah, that made a difference. It was a lot of thinking to do, but you know,
right.
now that you're explaining it, I think if it's yeah. So I think we did all right, but I'm just
Right.
scared for number 4 and 5. Let's see how those are.
All right. All right. Well, I'm hoping to teach people how these proofs go, right? We're trying to do proofs. And all right, so what's our next? Oh, all right, so we have to come up to the next question. All right, this one, question 4 is just proving that the supremum is 5. All right, it's kind of like the maximum, except it's not in the set. It's the smallest upper bound, right? So let's see. Here's our dense tree that we've parsed already, and then we have to parse the supremum tree. So it has an and, right? Because here's the and. We have 2 statements here, and so their one statement is we're given a value r prime, and then there's a blue exists, and then there's our statement. And on the other side, we're given a red for all, and then we're given our statement. So that's our 2 statements. So we need to prove it's a supremum that we have r equals 5. So you see for r, I automatically plugged in 5. And and S is already fixed too, right? So I made S green because we know what S is. So she's going to assure us that dense is true, and then she's going to give me an arbitrary. Oh, this guy over here, this adversary is going to give me an arbitrary value of r less than 5. All right, so there it is, an arbitrary value less than 5. And now then I have to come up with an x. And what do I need my x to be? I need it to be between r prime and 5, right? And I need it to be in the set. So really, to be in the set, it has to be strictly less than 5, right? So I just need some value that's strictly has to be strictly bigger than r prime, and strictly to be in the set has to be strictly less than 5, right? Now, conveniently, I have an oracle that will do just that for me, right? I give her 2 real numbers. Who do I give her? I give her r prime and 5. And what does she do? She gives me a rational number, because we're doing we're not doing rationals anymore. It could be a real number. It doesn't matter anymore. We're doing reals, but she gives us some value, and here she happens to give us a rational. It doesn't matter. She gives us a value in between. And when I first set up this dense rule, I had square brackets here, but I made it round, and I let you know that square brackets means that it doesn't include x and y, right? So she assures us that C isn't r prime and it isn't 5. It's strictly between, and right, and so what do we do? Oh, all right. So then what we have to come up with a value of x, and what is our value of x? It's the C that she gave us, right? She gave us that C. And what do we have to do is we need that C is strictly in this range, so that it's in S, and as needed, right? She told us that it's in this range, it's in the range, so we're done. Right, everybody buy with that? Right, then we have to do the other side, right? Now we're given an arbitrary value that's bigger than 5, and we just have to, oh, it's bigger than 5, so it's not in our set, right? That's it. Was that one hard?
I think that was the easiest question.
That one was easy, right? All right, and then question 6, right? Oh no, question 5. Question 5. What did I just say here? In order to prove a statement's not valid, you have to give one model in which it's not true, right? Right. This is saying, right, we have to prove it's that this statement that a supremum exists is not true over the rationals, right? We're trying to prove. All right, so we're over the rationals, and then we say here's a set. It's the set I gave you before, right? More or less before. So you didn't have to do. Hopefully, people got this set, right? It's the set of. Here's a set of rational numbers, right? All rational numbers that are less than the square root of 2. Well, what's the supremum of this? The supremum is going to be the square root of 2, right? Why? Because if you take any R value that's bigger than them, right? If smaller values of R prime, if you take any number that's smaller than R prime, right? It won't be a supremum because there are things in the set that are bigger than it. And if you take any R that's bigger than the square root of 2, it's not the smallest upper bound, right? I mean, I think from the previous question, we saw that the supremum has to be the square root of 2, right? But the problem is the square root of 2 is not rational, right? So does there exist, right? So the axiom is claiming that for every non-empty bounded set of rationals has a supremum, right? Here, this is clearly bounded. It's bounded by 5. I guess I didn't say that. It's bounded by 5, and it doesn't have a rational, right? Is that everybody good with that?
Yeah, Professor. So the way I started solving the question by parsing the statement as like having a parse tree, and then I said why this statement is invalid. Like my explanation was similar to yours. I had further clarification, but as well I provided a parse tree. Is that okay?
Sure. You can put in a parse. I mean, I could have put in a parse tree here, which I guess here I'm sort of just by hand waving. I mean, you'd really have to say why any value of R that's not the square root of 2, right? So here you can do a parse tree. Let R be something that's different than the square root of 2, right? And then you can play the game and see why R is not, this sentence is not true, right? So you could have done that, and I guess I could have put it, I mean, I guess the reason I did it short is 1, by this time I was feeling tired and exhausted and lazy, and 2, I stated in class, I think it was maybe even to you, that the way you do this is just by presenting a counterexample, right? So I guess you could have had a longer proof here to prove that it's a counterexample, but I got tired. How are people doing with these proofs? And I suppose nobody went on to question 6.